So the first talk of the today's session is presented by Toygun, BASAKLAR, right? And the title is Hypervector Design for Efficient Hyperdimensional Computing on Edge Devices. Toygun is a PhD student in the Department of Electrical and Computer Engineering at the University of Wisconsin-Madison. And his current research and interests all on wearable technologies, lightweight machine learning algorithms, and low power electronics, as well as reinforcement learning and health monitoring applications. Toygun, please.
Thank you. Thank you for the kind introduction. And I'm happy to introduce our work here today, entitled Hypervector Design for Efficient Hyperdimensional Computing on Edge Devices. So let's start with a simple question. What is hyperdimensional computing? So it is a lightweight, it's an emerging lightweight computing paradigm that draws inspiration from brain, and which also achieves competitive accuracy with the state-of-the-art machine learning applications for various applications, and it also achieves lower computational power. So why it is called brain-inspired? So the sensory input to the brain from eyes, from our nose, from our ears is believed to be dense, and inside the brain it is mapped to high-dimensional but sparse representation due to the large size of neuronal interactions. So let's say we heard a song, "Someone Like You" by Adele, and what we receive is the dense auditory input signals, and it is then represented as a high-dimensional signals in the brain. And with enough attention and rehearsal, the sensory information is stored in our memory, along with some other auditory inputs, let's say from some songs from Eric Clapton and Pink Floyd. And let's say 2 days later, we hear a similar or the same auditory input. Our brain immediately associates the sensory inputs with our memory, and we eventually recognize the song. So the hyperdimensional computing does a similar thing in its processing flow. It first maps the input data to sample hypervectors, to high-dimensional hypervectors called sample hypervectors, and this operation only involves simple vector arithmetic. So it's significantly cheap. So it only involves permutation, addition, and multiplication of d-dimensional vectors. And then the sample hypervectors that belongs to the same class are just linearly combined to obtain class hypervectors called class encoders. And this also just involves summation of sample hypervectors. And during inference, we again generate some query hypervectors. And basically the algorithm checks the similarity between these class encoders and the query hypervectors. And this operation only involves some multiplication or logical operations. So let's let F denote an n-dimensional input feature space, and let's say we have an S number of training samples in our dataset, and each training sample X sub S is an n-tuple. So what baseline hyperdimensional does is it first, using the training dataset, it first identifies the minimum and the maximum levels for each feature, and then it quantizes these feature space into M levels, M uniform levels. And then it assigns a random hypervector, random d-dimension hypervector to the first level. And the consecutive level hypervectors are generated by randomly flipping b amount of bits for each consecutive level hypervectors. And then the next step is construct the sample hypervectors. So using the training data sample, we first identify the which level hypervectors to be used, and then we fetch the level hypervectors from the step 1, and then we simply add them up to obtain sample hypervectors capital X sub S. And simply, as I said before, we just linearly combine the sample hypervectors that belongs to the same class to obtain a class encoder. Here it is denoted as E. And during inference, we simply generate query hypervectors using following the same procedures as in step 1 and step 2. and we simply check the similarity between these class encoders and the query hypervectors. So due to the simple bitwise operations, the hyperdimensional computing is highly parallelizable, and thanks to the large dimension, it is robust against noisy data, and it only requires single pass chaining. So these all makes HDC is a strong candidate for a lightweight learning algorithm. So on one hand, wearable IoT devices for remote health monitoring, especially for remote health monitoring, generally fuse data from multiple sensors for accurate real-time tracking, but they need to work on a tight energy budget due to the limited battery capacity, and offloading the data to the cloud is not an attractive solution because it increases the communication energy and raises some privacy concerns. So there's a need for light learning algorithm that can provide high accuracy, real-time inference, and robustness to the noisy sensor data. So it seems a perfect match, right? But there's a redundancy in HDC that we want to discuss today. So HDC requires large dimensions to achieve high inference accuracy due to this random mapping process. So a sufficiently large dimension is needed to ensure that the randomly assigned hypervectors for each feature are orthogonal to each other. Large dimensions implies higher energy consumption, longer inference time, and more hardware resources. So there is a critical need to optimize the design of these hypervectors, such that the performance of HDC is maintained or can be increased with using smaller dimensions. So our work presents a novel optimization algorithm for representing the input data points in the hyperspace instead of relying on the random mapping, and it uses a novel non-uniform quantization approach, and therefore we refine the distribution of these randomly generated hypervectors in the hyperspace. So to the best of our knowledge, it is the first technique that formulates hypervector design as a multi-objective optimization problem to achieve increased robustness, higher accuracy using smaller dimensions, as it can be seen from here. So let's start with a motivational example to show the significance of the proposed approach. And here we have 4 classes represented by 2 features. It's a simple 2D problem. And baseline HDC, although we are using 8,000 dimensions, it misclassifies a significant number of points around the class boundaries, as it can be shown from here, and the accuracy here is 91%. So in contrast to uniform quantization level, our proposed approach emphasizes the distinctive levels, and as you can see from this figure D, it actually, you can see it allocates the higher number of bits to level 6 here, the distinctive level, and level 16 here. And as a result, it achieves 100% accuracy using only 64 dimensions. So we also demonstrate a geometrical illusion, geometrical illustration using 2D TSNE graphs. Here in figure A, baseline HDC poorly separate the sample hypervectors for different classes, although it is using the higher dimensions. But our proposed approach yields a well-separated classes for the different classes with a significantly smaller number of dimensions. So it's just a motivational example, as I said. So how do we formulate our optimization problem? So we believe that the optimization problem, the optimized hypervector design should achieve 2 objectives. Spread the sample hypervectors from different classes as far as possible and cluster the same sample hypervectors of the same class close to each other. So in order to achieve these 2 objectives, in contrast to baseline HDC, which uses uniform a fixed value of B, which is the number of bits to flip at every consecutive level hypervector, we use a variable number of bits, and it is defined as the optimization parameters in our approach. This B matrix, it holds all the B values for every feature and every quantization level. And we construct the following multi-objective optimization problem. First, we want to maximize the accuracy, and second objective, we want to minimize the similarity between class encoders. So here it's actually a macro average recall, and we avoid to use total accuracy because it suffers from imbalanced data sets. And this equation here formulates the geometrical mean of each class encoder pair. And it is a lumped similarity metric for the class encoders. And we define the robustness in our work as 1 minus this similarity metric. So our problem is a non-convex optimization problem with integer constraints. So therefore, we employ genetic algorithm. And our aim is not only obtain the solution that gives the highest accuracy, but also improve the trade-off between the accuracy and robustness of the model. And since genetic algorithm maintains a population of solutions at every generation and is a highly explorative, we chose to use genetic algorithm in our work. Here, algorithm one describes the processing flow of the work. So input to the algorithm is randomly generated B matrices for each population, and for each population, we basically using these new B values, we generate level hypervectors, and using the level hypervectors, we again update the sample hypervectors and the class encoders, and we compute the accuracy and the similarity values. We also check the current feasibility of the current solution, and at the end, after some after a specific amount of generations, the algorithm outputs a Pareto front B and N by M set. So we implement our algorithm in MATLAB using population size as 1,000, and we run at least 200 generation for each application. So we evaluate our approach on 4 publicly available representative health applications. The first one is Parkinson's disease digital biomarker dream challenge dataset. It involves some walking tasks with expert labels that states if the patient has Parkinson's disease or not. The second one is EEG error-related potentials dataset, which provides 64 channel EEG recordings from 6 subjects to study error-related potentials. The third one is human activity recognition dataset. It provides stretch sensor and accelerometer readings from 22 subjects while they are performing 8 activities. And the last one is the cardiotocography dataset, which provides 21 features from various of cardiotocograms, which are extracted to diagnose the fetal state. And the fetal state is divided into 3 classes: normal, suspect, and pathological. So we first, we didn't use same dimensionality for every application. For each application, we first sweep the dimensionality of the hyperspace to decide the dimension to be used in the baseline HTC implementation, and for each dataset, and then the proposed method is used to minimize the dimensionality. For example, in PD challenge datasets, the baseline HTC implementation gives 85% accuracy using 2,000 dimensions, but our proposed approach gives 86% accuracy using only 32 dimensions. And similarly, the proposed approach significantly reduces the dimensionality and improves the accuracy of the model, as can be seen from here. We also apply a lightweight learning algorithm, SVM, as a comparison point, and HTC seems to achieve, again, competitive accuracy with SVM too. So robustness in our work is measured by the similarity between class encoders and defined as 1 minus average similarity, as I discussed it before. So here, this figure shows the Pareto front solutions in terms of accuracy and this similarity metric. For example, the accuracy and the robustness for this EEG-RP dataset using 2,000 dimensions is 70% and 0.017, and the proposed approach improves the accuracy to 86% and also the robustness to 0.05, 0.035, and it can also trade off the accuracy to improve the robustness to as high as 0.08, while still achieving the higher accuracy than the baseline HTC, as can be seen here. Similarly, the proposed approach improves the accuracy and the robustness for other datasets too. In summary, our approach provides a set of hypervector designs to choose from according to the nature of the application. So we also evaluate the proposed approach by running inference for all applications on AutoRadix U3 platform. The applications run on a single little core, a 7 core with lowest frequency setting, since this setting is the closest configuration to a computation limited edge device. And these figures compares the baseline HTC and the proposed approach in terms of model size, power consumption, and inference time. And we achieve a significant amount of reduction in model size and inference time, as it can be seen from here. And eventually, overall, it achieves more than 66 times energy efficiency, and it reduces the model size to around 100 kilobytes. So IoT applications require lightweight learning algorithm that can achieve can provide high accuracy, real-time inference, and robustness to noisy sensor data. We also explained that there's a critical need to optimize the design of hypervectors such that the performance of HTC is maintained with smaller dimensions, maintained or increased with smaller dimensions. So here we presented an optimized hypervector design approach to achieve higher accuracy and robustness using a smaller model size. And evaluations on our on 4 health application data sets shows that we can achieve more than 1 order of magnitude reduction in model size, inference time, and energy consumption, while achieving increased accuracy. It also optimizes the trade-off between accuracy and robustness of the model. So as a part of our future work, we plan to evaluate the proposed technique on low power embedded processors and custom hardware accelerators, and also it will be a part of our platform called Open Health, and you can learn more about it using this link, through this link. Thank you so much for listening.
Thank you, Toygun, for a great talk. The floor is open for questions. So while waiting for questions, I have one quick question for your slide. I guess it was slide 12, that you were comparing the application's accuracy. Oh. Yes. Yeah. So for the SVM, you mean support vector machine, right?
Yeah.
Right. So that part I didn't understand with the compare with the baseline and proposed, because SVM, you need to do all the basically, again, it's a basic classification, feature extraction. You just ran again the same data with that classifier, and you're just comparing your method with that.
No, we are using the like the original input features with SVM and compared to that. Yeah.
All right. Okay, sounds good.
Yeah.
All right. There is no other question on the floor. Well, thank you very much again, Toygun. That concludes our session, and I will ask the chairs to conclude the conference as well. Thank you.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs, Green Waves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.